Welcome back, and let's begin Physical Science, Module 13A. We're still working on the forces in creation, and we'll be talking about atoms. Larger vocabulary list this time: protons, neutrons, electrons, antineutrinos, learning about the Bohr model, nucleus, isotopes, quantum mechanical model, atomic number, radioactive, mass number, and element. So let's talk about the structure of an atom. I'm sure you've seen this picture before. It shows the nucleus of an atom, and inside that nucleus are protons and neutrons that are tightly held together. And then on the outside of the nucleus are electrons that are in orbitals around the nucleus. The protons, I've listed their basic sizes in retrospect to each other. These numbers are basically unpronounceable. That's why we use scientific notation. But essentially, neutrons are about 0.14% heavier than protons, and protons are about 2,000 times heavier than electrons. Protons and electrons attract each other. This is something we've learned before, and that's one of the things that holds them, the nucleus, together, and also attracts the electrons. So the atoms are made up of these three smaller particles, and they all have different properties. There's an important difference between protons and neutrons. Firstly, neutrons have no charge. Because of that, they're not a stable particle, so they tend to be less predictable than our protons and our electrons are. A neutron that is not part of an atom will eventually fall apart. So I don't know if you realize this, but there are neutrons floating around that might not be part of an atom. So if they're not part of an atom, they don't last very long. They'll either become a proton, an electron, or an even smaller particle, call it an antineutrino. But once the neutron becomes part of the atom, it will stay as a neutron while it is in the atom. And although we can't see atoms, we can produce a model of what we believe an atom looks like according to its properties. So what's a model? What am I talking about when I say model? Well, it's a schematic description of a system that accounts for its known properties. So when you think of models, you usually think about models of cars or something like that. But in science, we often have to model things that cannot be seen. So you learn how they work and how other things in nature previously exist, and we formulate ideas of what we think models look like. A good model can accurately reproduce the known properties of the system being modeled, and the model can be used to give us a mental picture of what the system might look like. So here's an example of a model of an atom. This is what we call the Bohr model. Until recently, this was thought to be a very good representation. Proposed by Niels Bohr in 1913, it was the first model of the atom that could account for the known properties of the atom. So here you see the identifiable nucleus that contains the neutrons and the protons, and then you have these outer shells that contain electrons, and these shells are actually balanced, and you can only have a certain amount of electrons on each level of a shell, and that's something we'll go into in a little bit. In the Bohr model, the neutrons and protons are packed tightly together in the center of the atom, called the nucleus. Electrons are not in the nucleus, they're outside of the nucleus, and the electrons orbit the nucleus in ellipticals or circles. And think about how our planets orbit the sun. It's a similar idea. While the electrons orbit the nucleus, they're moving with a specific velocity, but at the same time, they're attracted to the positive charges from the protons in the nucleus. This should sound familiar because we talked about before about attractions and how that attraction provides a centripetal force. So the centripetal force changes the direction of the electron's velocity. Without that force, those electrons would just fly off, producing circular motion. So the electrical attraction between the protons and the electrons allows the electrons to travel around the nucleus in an orbit. In actuality, the Bohr model is partially incorrect. It's used because the quantum mechanical model that actually is used in science now is extremely complex. It's so complex that most people cannot do the math behind the quantum mechanical model. The main deficiency of the Bohr model is its electron orbit. The electrons, in actuality, do not orbit in fixed circular orbits. The orbits are actually interesting shapes, and that gets into just too much depth for us to demonstrate here. The Bohr model also can't be drawn to scale. In the models that we see, the electrons are actually too large, and in reality, the electrons are really much farther away from the nucleus than pictured. So an example in your text was a tiny marble in the middle of a baseball stadium. So the upper seats in the stadium would be the electron orbits, and that is quite far away. Another thing that they know is that there is nothing between the nucleus and the electrons but empty space. In fact, atoms are more than 99.99999% empty space. And because atoms make up all of matter, matter is mostly empty space. Now, don't be surprised if in the future there's other things that they tell you are happening in that empty space. The atom is extremely complex. The attraction between the proton and electron keeps the electrons in orbit around the nucleus. The electrical charge of an atom is zero because atoms are balanced. They have an equal number of protons and electrons. So this is very important in nature. Even though the proton is 2,000 times more massive than the electron has enough negative charge to balance the positive charge of the proton. Can you imagine designing something so seemingly off balance? Well, this is how some things work in nature. They're actually balanced in a way that we as human beings would never think of. If we were to balance something, we'd always think of the scales, having something on one side as heavy as something on the other side so that they could even out. If even 1% of those charges is different, the resulting electrical imbalance would cause a sizable amount of matter to instantaneously explode. So let's talk about the atom. And the number of protons that an atom contains is what makes it the type of atom it is. So here's a picture on the element chart of helium. Helium, its atomic symbol is He. Many of the symbols will look like the words they are, but some won't. So this is something in chemistry that you would have to memorize. Helium has 2 protons. And the number of protons is what we call the atomic number. So on an elemental chart, you'll see a number above the atomic symbol. That will be called the atomic number, and it will tell you how many protons is in that atom. If an atom has 6 protons, or an atomic number of 6, it would be a carbon atom. This atom has 2 protons, so it is a helium atom. The number of neutrons in an atom is not listed. That's because neutrons actually have a minimal effect on most atoms, though the number of neutrons does add some mass to the atom, and an atom that has too many or too few neutrons will become radioactive, and that's another discussion. It's still important to keep track of the neutrons because they're actually measured in the mass of an atom. So the mass of an atom is the sum of the protons and neutrons in the nucleus of the atom. And if you look at this picture again, you'll see it says that helium atom has a mass of 4.0. So if we know that the mass is 4 and the atomic number or the number of protons is 2, we can say that 4, the mass, minus the number of protons, which is 2, equals 2, which is the number of neutrons. So even though we don't state it on the chart, we can figure out how many neutrons there are. So to review that, the atomic number equals the number of protons, the mass equals the protons and the neutrons together. If you need to solve for neutrons, that would be mass minus atomic number. So this atom has 2 protons and 2 neutrons and would be called helium-4. Now the reason why they call it helium-4 is because atoms can sometimes have different amounts of neutrons in them, and so they'll be named a little differently. So here's an example from your text. We have helium-4, which has 2 protons, 2 neutrons, and 2 electrons. But we have helium-3, and that has 2 protons and 1 neutron. And helium-5 has 2 protons and 3 neutrons. You can see that all 3 of these atoms have 2 protons and 2 electrons. It's the neutrons that have a different number. Because they have a different number, they'll have a different mass, though each one of these will have similar properties. So helium with a mass of 4, which is 2 protons and 2 electrons, is called helium-4. This next one would be called helium-3, and the third one would be called helium-5. So here's an example. The helium in a balloon actually has different types of helium inside. The balloon will usually contain both helium-3 and helium-4. Because this is a collection of atoms, we give it a different name. So a collection of atoms that have the same number of protons, so meaning the atoms inside, we have helium-3 and 4, even though they have different mass numbers, they have the same number of protons. We call that collection an element. So an example would be carbon, which we think of as coal, and it's an element that actually contains carbon-12, carbon-13, and carbon-14. So here's an example from your text. It says there's an element, nitrogen, that has 7 protons. If a nitrogen atom has 8 neutrons, what is its name? And how many electrons does it have? So I gave you a representation here with 7 protons and 8 neutrons. And you can see that there are 1, 2, 3, 4, 5, 6, 7 electrons. So the answer to A, if it has 8 neutrons, what's its name? Well, a nitrogen atom that has 7 protons and 8 neutrons will be nitrogen-15. Remember, we add the protons and neutrons together. And B, how many electrons does it have? Well, this atom needs to balance out. So if it has 7 protons, it will also have 7 electrons. So if you have any questions when you're doing your on your own problems, please contact me, and we'll talk again. in Module 13B.